In previous videos, we've seen that we can use areas to estimate or find exactly the definite integral. In this video, we want to work backwards. That is, we want to find an area using the definite integral. Okay, so how do we do this? Here's an example. I have a curve y equals 2 minus x squared and y equals 0. And what I'm interested in is the area between these two curves. That's this area here. So I want to find this. And the way I'll do it is I'll express this area as a definite integral, and then I'll use my calculator to figure out what that definite integral is. Okay, so in this case, what I want to integrate is this function. This function is given by 2 minus x squared. The area between the graph and the x-axis is the definite integral 2 minus x squared dx, where I vary x between this point, this will be my first endpoint, and my second endpoint. So all I need now is to find these two endpoints. Where do those endpoints occur? It's when 2 minus x squared is equal to 0. That's the x-intercepts for this function 2 minus x squared. That happens when 2 is equal to x squared, or in other words, when x is either equal to the square root of 2 or x is equal to the minus square root of 2. That is, these points happen at the square root of 2 and minus square root of 2. Now once I find these points, those become my limits of integration. Okay, so there I have it. I have expressed this area in blue with a definite integral. And now I can use my calculator to figure this out or estimate it. So I use my calculator. It gives me back a value of 3.771236 blah blah blah. So basically the area between these two curves is about 3.8. Okay, let's move to another example, a little bit more complicated. Here I have two curves and both are not the x-axis. And I would like to find the area between them. So I'd like to find this area here. Now, how do I find this area? Well, the observation is that in finding this area, I could use Riemann sums where the heights of the rectangles are the differences in the heights of the function g and f. In particular, the height of each rectangle, I have little tiny green rectangles, the height of each rectangle is about g of t minus, or sorry, f of t minus g of t. Why do I put f first? Well, actually, in this case, f is above g along this interval. So here's my function f, and it's above g, so I want something positive for my heights because I want a positive area. So I have f minus g. That'll be my height of each rectangle, then I multiply by delta t to get my rectangle, and I'll sum these up. If I take infinitesimally small rectangles or thin rectangles, I'll end up with a definite integral. That is, I'll get something that looks like this. So what's the upshot? The upshot is, if you want to find the area between two curves, take the difference between the two functions and integrate that. Now where do I want to integrate it? I want to integrate it between here and here. That is, in terms of the x-axis, I want to integrate between here and there. So what are these 2 points? Well, these are the places where my integrand, the thing I'm integrating, is actually equal to 0. So that's where x squared, x minus x squared is equal to 0. That's my integrand here. And that happens if x times 1 minus x is equal to 0. And that happens if x is equal to 0 or x is equal to 1. So these points, this is x equals 0, and this is x equals 1. So my limits of integration are 0 to 1. Okay? To sum up, the integral I want to consider is the integral from 0 to 1 along this interval of the difference of the top curve, which is x, minus the bottom curve, x squared, dx. Okay, so I've expressed the area as a definite integral. Now I could use my calculator to figure out what that number is, or at least an estimate. And my calculator tells me it's about 0.16666 repeating, it appears, 7. So that's my estimate for what this area is. It's a pretty good estimate given by my calculator. One more example. In this example, we're not actually given the graphs of the functions. We're just given formulas for the functions. Y is equal to square root of t minus 1 and y is equal to 2 times t minus 1. And we're asked to find the area between these curves. So what I suggest in this situation is use your graphing calculator to graph this function and to graph this function. Graph both, and you can graph them on the same set of axes. You can find out where they intersect. We could have done that in the previous examples as well. If you do that, you should get a graph that looks somewhat like this. Okay, and then when you, that's the graph for y equals square root of t minus 1, the first one. And if you graph the other one, well, y equals 2 times t minus 1 is just a line with slope 2. And so you end up with a graph that sort of looks like this. And what we're asking for is the area between those curves, meaning this area. That's the area bounded by the two curves. And so that's going to be an integral. In this case, the function that's on top along this interval is square root of t minus 1. So that goes first. Then I subtract from that the other function, 2 times t minus 1. And then I do dt. Finally, I need to figure out what the lower limit is and the upper limit is. So for the lower limit, that can be found to be equal to 1. That's not so hard. And for the upper limit, well, that we can get by setting this equal to that. That is, when the integrand vanishes, square root of t minus 1 is the same as minus times 2 times t minus 1. So we want square root of t minus 1 equal to 2 times t minus 1. Okay? You can use your graphing calculator to estimate this as well, but we're going to do it here algebraically. So I'm going to divide both sides by the square root of t minus 1. So I get t minus 1 divided by square root of t minus 1. And then on the other side, I divide by 2. So I'll get a 1/2. Now what's nice about this is that t minus 1 divided by the square root of t minus 1 is the same as the square root of t minus 1, right? Because t minus 1 is equal to the square root of t minus 1 squared. So this is equal to 1/2. Now I can square both sides and I get t minus 1 is equal to 1/4, because 1/2 squared is 1/4. Then I can add 1 to both sides to get 1/4 plus 1 is equal to t. 1/4 plus 1 is the same as 5/4. So that's where this point occurs. This one was at 1, this one is at 5/4. Okay, so now I can apply my definite integral. What do I have? Well, for your calculator, you would write 1, and then 5/4 is the upper limit. That's what we found here, times, well, in the calculator, you would probably write something like this. X minus 1 to the 1/2, right, minus 2 times x minus 1, and then you'd have a dx. Okay, so this would be the expression you put in your calculator, and when you do, what you should get out is 0.02003, etc., etc. So this is a pretty good estimate. It's telling us that this is pretty darn thin. It's only about 0.02, this area.